So we are looking at a particle has been accelerated east through a potential difference of 240 volts. All right. This one I'm going to go ahead and draw it. All right. So if I accelerate a particle through a potential difference, generally speaking, what I've got is a parallel plate system. Okay. And here's my particle. It's been accelerated east. All right. Then it exits this field. So we must have some kind of field here. And it goes through a little hole in the other side of the plate. Okay. It then immediately enters a magnetic field that is directed north. All right. So I guess I'll put some kind of magnetic field here. All right. Like this. That's directed north. And where our vision is from above here. All right. That's what we're looking at. It's from above. So basically that's east and east there and north there. All right. Okay. It then immediately enters this magnetic field. The particle then comes back and it hits the plate 0.3 meters above the exit. Okay. All right. So here was the exit. And so it must come. Well, I know that basically if I want to figure out what happens to this particle, this is a magnetic field out here. Okay. This is a magnetic field. If I want to figure out what happens to this particle, I point my fingers in this direction. I point my thumb in that direction. And then according to the right hand rule, the force that it experiences would be up, right? Would be up. So that's north, that's east. Remember, up would be towards us, out of the screen, okay? So basically what happens is this thing comes out of this exit and flips towards us and then comes back and hits the plate here, okay? And it happened at 0.3 meters above the exit. So now what I'm going to do is I'm going to basically kind of build a side view. All right. So we have the same thing basically here. And we've got, but this is now from the side and it comes out and goes up like this and hits. Okay. And so I can't draw that from here because it basically kind of comes out and then goes up and hits. All right. That's kind of the idea. All right. Because we've got some kind of magnetic field here that's pointed north. Now, this 0.3 is a key number because what it does is it gives us the radius of curvature in the magnetic field. So that's going to be a key value. So my radius of curvature is 0.3 divided by 2, or 0.15, okay, meters. And now let's write down some other stuff. The potential difference that it goes through is 240. All right. That's going to be helpful. And let's see. We know that its mass is 1/3 that of a proton. All right. And so I'm going to write mass of the proton divided by 3. All right. And we know that the magnetic field is equal to the same that we found in question 2. So going back to question 2, if we remember that one, that was a coil, right? That was a coil that had 2 amps running through it. So there's my 2 amps where I is 2. And it had the length of the coil was 25 centimeters long, so 0.25 meters, and that goes here, right? And let's see, what else did it have? Oh, it had 250 turns, and so the number of turns was 250 turns, okay? And so that goes there, okay? And then don't forget that we had the mu naught, which mu naught is equal to 4 pi times 10 to the 14. I said that wrong. 7. okay? And basically now what we're looking at is we've got all sorts of information. The question is now, what is the charge of the particle, okay? So I want to find what's the charge, all right? So the way that we're going to be able to do this is we're going to say, well, look, I know that this particle is in a magnetic field. And I know if I take the force magnetic, it's QVB sine theta, okay? And there it is. That's going to be our charge, all right? So basically, this is now my equation. Now the question is, well, how am I going to get force magnetic? I've got B, it looks like. Here's B. Velocity of the particle. Interesting. I think the velocity of the particle is going to be dependent on the potential difference, okay, that it went through over here. And remember also that force magnetic is equal to the centripetal force, okay? And so I'm going to go ahead and write down that this is equal to the centripetal force, because remember that particles, charged particles, while in a magnetic field, move in a circular path. And remember that the centripetal force is equal to the mass of the particle, which is the mass of the proton, divided by 3, which is over here. I'll put that in a little while, times the centripetal acceleration, right? Sine theta. Remember, though, that the centripetal acceleration from our circular motion unit is v, velocity of the particle, squared over the radius of the pathway, which is going to be this value over here that we ended up discovering. And so I've got QVB sine theta. All right. And now, essentially, taking a look at this, I've got Q, right? And I'm going to go ahead and solve for it. I'm going to pass all this other stuff down over to the bottom. According to algebra there, I'm looking at Q, which I'll write on this side now. Maybe I'll start this in orange now, because I finally solved for Q, is equal to mv squared over r, and then I've got a vb sine theta, right? Don't forget that this v will cancel with one of those, and so effectively what we're looking at here is m v r b sine theta, okay? Awesome. And so now, essentially, well, maybe I'll write this down here now at this point. The mass, I'm basically using this formula right here. The mass, remember, is one third that of a proton. So I'll go ahead and write that down, right? So my mass is mass of the proton divided by 3. I'll put the 3 on the bottom. The velocity of the particle, oh shoot, I don't know that yet. Let me write that down. So let me figure that out. I'll figure that out up here. The radius of curvature is 0.15 meters. So I'm going to go ahead and write that down, 0.15, okay. Meters, I won't write the units here. The magnetic field is B, which is current, which is 2. N, which is 250. This is this guy, which is the permeation of magnetic permeability of free space, which is this number, 4 pi times 10 to the 7, and the length, which was 0.15, right? So I'll go ahead and write that stuff down here. That's my magnetic field, okay? And it's going to be, what is it going to be? 2 times 250. Oh, I didn't give myself enough space here. I'll zoom in a little bit. 2 times 250. And then what was it again? It was free space over length, all right? Length was 0.25, okay? And the magnetic free space is 4 pi times 10 to the 7, okay? And basically, that's now what I'm looking at. And I also have a sine of theta here. And we have to figure out what theta is. Okay, so let's look at this. let's currently figure out theta, okay? That's what we're going to figure out now. And in a moment, we'll figure out what velocity is, okay? That's our last variable we got to figure out. The mass of the proton, we all know that one, all right? So basically, in order to get the theta, we remember that that's the angle between the velocity of the particle and the magnetic field, okay? And so we know that our magnetic field is going north, and our curvature path is up like this. And so we're looking at 90 degrees, okay? Let me again just explain that again. Remember, our magnetic field is kind of going north, which in the side view would be field lines like that. And if you look at it, what's the angle between this velocity vector and a vector that goes into the page? It's 90 degrees. So imagine into the page and, east, 90 degrees. Into the page and north, 90 degrees. Into the page, and the angle between into the page and northeast is also 90 degrees. And so we're looking at a 90 degree angle always. So I'm going to go ahead and throw 90 degrees in there. Now the question is what's the velocity? Remember, the velocity is obtained because it's accelerated through an electric field. And so we know that the change in electric energy is equal to the change in kinetic energy. And so we know that the potential difference, right, times the charge, right? So we've got potential difference times the charge is equal to the 1/2 mass of the particle times its velocity squared. And this is the velocity that the particle has right here after it exits this field. And that is the velocity which we'll place right there, okay? Well, that's dependent on, well, let's go ahead and solve for that. So we're going to get a delta VQ multiplied by a 2, divide by the mass of the particle, and this is square rooted, and this is going to be my velocity, which I'll go ahead and throw right in here. Since it's got a square root, I guess I don't need the parentheses. So there we go. We're talking about the square root of 2 delta V, which is 240, Q, O, which is basically what we want to find, right? Is Q right there, okay, over M, okay. And I just actually realized I solved for Q right there, but now I've got another Q over here. Uh-oh, what are we going to do? Okay, so let's go ahead and deal with that, because now, look, we can't solve for Q, or we've solved for Q, but we have a Q over here. All the rest of this stuff we know, all right? And so this is by the way, the mass of the particle is going to be mass of the proton divided by 3 right in here as well. I'm zooming in on this equation. So you might be saying, oh, shoot, this equation looks pretty wild, but it's actually not, because this is 1, this sine of theta, so I'm going to erase that. Sorry, sine of 90 degrees is just like that, right? And now I'm going to try and get this Q isolated here. What I'm going to do here is I'm going to pull this Q out of here, and I'm going to write it as a square root of Q, all right, right there, all right? And then I'm going to go ahead and divide it over like this. So we've got Q over the square root of Q is equal to mass of the particle times the square root of 2 times 240 over mass of the proton divided by 3, still over 3 times 0.15, and I've got 2 times 250 here, 4 pi times 10 to the 7 over 0.25, okay? And there is our our solution, more or less. This is going to be a bear to type into the calculator. And so what I'll probably do is I'll pause the video and I'll type it in while on pause, because it's going to take me a while to type that guy in there. All right, and I'll be right back. Oh, before I do that though, you might be saying, well, what is this? This is Q over, Q, right? Q over root of Q. So I haven't solved for Q. I've got Q over root of Q. We got to get these guys together, all right? In order to get these guys together, you realize that basically what you're looking at is Q and Q to the 1/2, which could be written as Q to the 1 minus 1/2, which is actually just the square root of Q, right? Because it's Q, this is Q to the 1. Remember, there's the rule that says something divided by something, you can subtract the exponents if the two bases are the same, okay? And so I've got 1 minus 1/2, which is just 1/2. And so I'm looking at the square root of Q over here is equal to all of this stuff right in this area, right? Which is what I want to figure out, stuff, all right? And so basically, once I figure out all that stuff, I'm going to go ahead and square it both sides. So Q, right, is equal to the square of all of this stuff. And remember that this stuff is just the guy in the calculator here, okay? Whatever I get with all this stuff in the calculator, which, like I said, it's going to take me about a couple of minutes to get that. Hold on. Let me pause this, figure that out. Pause. All right, so there it is. Oh, I got to square this still. I forgot to square it. Basically, I ended up getting the numerator 1.55 times 10 to the negative 12, okay? And the denominator, I got all that stuff. Oh, by the way, I messed up here. This is times 10 to the negative 7, not 7. I forgot my negative. And there you have it. So I divided these throughout. I got 1.37 times 10 to the negative 9. And I forgot to square it. So now just square that. And that's the mass of that particle. All right. So again, back to this guy here. All right. Here's the answer. Square it.